So we continue on the topic of interference, and we'll look into Michelson interferometer and Mach-Zehnder as well as Fabry-Perot interferometer. As we define, an optical interferometer would be an instrument that can generate interference fringes arising from optical path differences. So at least we need at least two beams that will travel different optical paths, and then when they are brought together, they would have some optical path difference between them, in which they will then be brought to interfere and create the interference pattern. There are two main classes of interferometers: the wavefront division, example of which we have described in the Young's double slit, and the amplitude division interferometer, whereby the amplitude is divided by using a beam splitter. And the thin film interference pattern that you see from a thin film is an example of the amplitude division. And now today we'll look into Michelson interferometer. This is a simple arrangement for Michelson interferometer. Now we will have a light source, and the initial beam will then hit this beam splitter. Now this first surface of the beam splitter is partially reflecting and partially transmitting. And then the reflected beam 2 will then go to the mirror, assuming C is not there, which is called the compensator, and get reflected back. And then it gets transmitted through the beam splitter, and it gets to your eye. The transmitted beam here, it travels through the beam splitter, goes to mirror 1, gets reflected, passes through the beam splitter, and then get reflected, which is an internal reflection here, and then it passes through the beam splitter over here and interfere with the other reflected beam, and the two beams will create interference pattern. So looking at this, now if you compare this beam and this beam that comes to 4 here would have passed through the beam splitter once, whereas this beam 3 here passes through once, and then twice, and then a third time. So which means that beam 3 here has made an extra 2 paths to through the beam splitter. So in order to compensate for this extra path such that it will be easier to equate these two optical paths, we place a compensator here which has equal thickness as the beam splitter, usually the same material, and is placed parallel to the beam splitter here. Now let's look at the path of the beams. Just now we had this arrangement. So if we look into the phase shift due to reflection, we have one external reflection here. Initially already has one here, so in total the blue beam here would have undergone 2 external reflection, so the total phase shift will be 2 pi. Whereas the red beam here would only undergo 1 external reflection here and 1 internal reflection. Now internal reflection will not have any phase shift, so in other words, this red beam here would have undergone just pi shift. So comparing these two beams, there would be a relative phase shift of pi. In this scenario, where the reflective surface is over here, if I've gone through, they started to split here, but this beam would have an internal reflection, external reflection, and then it goes and gets collected here. But the blue beam here would then go through here and gets reflected here. So one external reflection, and then it gets another external reflection. So in total, the relative phase shift between these the red and the blue beam would then just be pi, or a half lambda distance, optical distance here. You see that this mirror is movable. This can be moved, and the other usually can be tilted slightly. This is an example of the Michelson interference fringes. In this case, white light is used, and you can see that the interference of white light is white, and you can see that it's about 2 wavelength difference. Now, if you would like to do some mathematical, or rather get an expression for us to predict and calculate whether we are getting a dark fringe or a bright fringe, so what we have to do is then align all the beams in one line, sort of, or rather one direction, or vertically in that sense. So what we do is we're going to rotate the source towards here. As you can see now, the source of light comes from this position. Now this angle is a little bit exaggerated because we want to show it clearly. And then whereas the mirror 1 now is rotated to be over here, as you can see, the mirror 2 has a mirror prime here to show its virtual position, and it is placed here. Well, we can think of it as being slightly nearer than M2. So now what we're going to do is look at the ray. Basically, we're going to take this ray from the source, and then basically what happens is a reflection from mirror 1, a reflection from mirror 2, and they're brought together again. So here we have the first reflection at mirror 1, the virtual mirror 1, and then it goes into the eye here. And then it goes on, this one is the one that's reflected from mirror 2, and it goes to your eye. Now the distance, let's say the path difference, the position of the mirror is such that there's a difference d between the two mirrors here. So upon reflection, if you look at the image for mirror 1 prime, the image plane is S1 prime. For mirror 2, the image plane is S2 prime. Now this being d, then this will be 2d, because you have this equal distance from here to here. Then for this one, you have an equal distance from here, an equal distance back, and that makes this 2d. Now, if you look at these two beams here, you see that the optical path difference would be delta p here. Now, this is 2d, this is angle theta, so the optical path difference then is given by 2d cosine theta. We see question 1. Why is the compensator inserted? So please make your answer in spectrum. Let's assume that they have equal amplitude, the two interference beams have equal amplitude, then the variation intensity will then be given by this, which we already obtained from the previous lecture. But this has to do with the phase difference that arises from the optical path difference. Okay, and if we incorporate the phase shift due to reflection, then we would have a relative net phase difference between the two beams, and that would be equal to pi, which is equivalent to lambda over 2. So adding the two together for a dark fringe, we will have 2d cosine theta plus lambda over 2, equate that to half integer lambda. So we have m plus half lambda. Now this cancels, so we come to a simple expression, which is 2d cosine theta equals to m lambda. Now, if the fringe is such that the center is a dark fringe, which means that at the center, cosine theta will be 0, cosine theta is 1. So we will have m equals to 2d over lambda. Now that would give you, actually, it will give you the maximum m number. And if you look at this expression here, if we write m equals to 2d cosine theta or lambda, you see that as lambda increases, which means that you are looking further from the center. Let's go back to this to show you. When theta increases, that means you're viewing further away and further away, or rather reflected beam become further away. So you're actually viewing those fringes that are further away from the center. Then you find that the order would then decrease according to this expression here. So, well, we would prefer that at the center, m is equal to 0. So we just do a simple mathematical expression here. We have a maximum number minus m. So if that m is also a maximum number, then p equals to 0. So that would represent the center dark fringe here. So what we do is to take the maximum m minus m here. So, and from here, if we want to substitute equation 3 into 2d cosine theta equals to m lambda, so we replace m with 2d over lambda minus p, and that's equal to 2d minus p lambda. So in other words, p lambda will then be equals to, there's a common 2d here, into cosine minus, or rather cosine minus 1, but because it's negative, so that is exchange, it become 1 minus cosine theta. Then if you look at if you look at this fringe here, now we said that the position of the fringe here will be defined by the angle. So let's see, let's differentiate this equation. So we get negative 2d sine theta delta theta equals to delta lambda, delta m multiplied by lambda. So we concern just about the change in the angle. That means as you shift from this position to the next and to the next. So that will be equal to lambda delta m. So if you would shift from one position to the next, that delta m would just be 1 and divided by 2d sine theta. Now this delta theta, meaning that if you want this to be larger or the fringe to be wider, to be spread wider, then we would want the numerator value to be higher, but we are talking about the change of just the shift of just one order. And if this number here is smaller, that would mean that delta theta will be larger. So if we use one wavelength, longer wavelength, this will be larger. If you use smaller d, that means the separation between distance between the two mirrors is smaller. In fact, if they're very close together, then this will be very large. And or if sine theta is small. Now, if sine theta is small, it means that theta is very near the center. Well, that's why if you look at this, here they spread wider and then it gets narrower and narrower. So now, and if we were to translate the mirror such that delta d is changed, then you find that if you look at this and if you assume cosine theta to be close to, theta is close to 0, so cosine theta is close to 1, then if the mirror translate a distance of delta d, that would mean that our lambda is fixed, so we have a change in the order. So you see the fringe shifting. If you look at just one position, you can see the fringe shifting over that particular position. And from this relation, we can then use this relation to measure lambda when we know what would be the distance translated by the mirror, or rather the difference in d of the mirror. Here is question 2 that you have to answer in spectrum. Will the fringes be spread wider if we use blue light instead of the red light? Well, the red light we mean is this one that we see here. Okay, this is an example of a question which I think you can read on your own. Okay, let's look into application of a Michelson interferometer. So it can be used to measure thin film, as we had seen in preceding lecture, which was on what is that, interference due to thin film. Now, and it can also be adapted to measure the refractive index of a gas. But what we do is we insert a cell that contains gas into one of the arm here. So that would bring about, because of this, there's a change in the optical path. So that change is reflected as this, and it will be equal to the optical path length when the gas is there, and L, minus when the gas is not there, the distance is basically just L. So this will be the change. Now back to the previous equation of where we work as delta M equals to 2 delta T over lambda. So using that, we now substitute for delta T with L and minus 1. So what we have will be, then we will be able to actually measure the refractive index of this gas from here. So n minus 1 equals to lambda delta M divided by 2D. So here is related to application 2. Here you can see the fringes of a candle flame. Because the density is different, the refractive index will be different, and you can see distorted fringe pattern here. The third example would be if you have two lines which are two optical lines which are very close together. For example, the sodium lines, whereby if you look at this is 588.99, this is 589.56. The difference is about 0.6 nanometer, right? 0.6 nanometer. So then we take one wavelength, and you find that there would be a set of interference pattern that correspond to wavelength 1. There would be another set that correspond to wavelength 2. Now these two sets would then sort of overlay over each other. Now, but as we move the distance d, then this overlay will start to move until at one position they would then be matching with each other, and then you see very clear fringes. And then as you change the distance, you start going out of phase, then you see all blurry, and then they start to be aligned again. So that's how it works. So now for a fixed path difference d, then we are going to that is when they are aligned here, then you see m lambda equals m prime lambda prime. Okay, let's consider first coincidence, and these two sets of fringes at the point at that coincidence. The path difference is the same for the two sets, which is we shall give the distance value of d1, but this set for d1, it has an order of m. This set for d2, it will have m prime plus 1. This one corresponds to this wavelength. So now n must be an integer. If we take, for this case, the optical path difference is taken to be d1, then from equation 9, which is this one here, then we will have this order 2d1 over lambda will then be equals to 2d1 because they're the same divided by lambda prime plus n. Now at the second coincidence, that's when the difference between one set has got shifted by 1. So assuming 1 to be constant and that one is shifted by 1. So we will then have, let's consider this to be shifted, then this becomes n prime plus n plus 1. And this happened at a distance d2. So it's 2d2 over lambda equals to 2d2 over lambda prime plus n plus 1. Now then we are going to deduct these two equations. And then subtract, alright, deduct or subtract. This one, we deduct this from here. So then we will have now 2d2 minus over lambda minus 2d1 over lambda, and that will be equal to 2d2 over lambda prime, yeah, minus 2d1 over lambda prime plus n plus 1 minus n. So we have it here. So in other words, what we have will be now 2 into the difference, the distance, the difference in the distance between the mirror. Then it would be equal to what we have here. So we will have 2 delta t over here over lambda prime plus 1. So let's then we can also write it as 2 delta d plus lambda d over lambda prime over lambda prime. Now lambda and lambda prime are very close, so delta lambda can then be approximated as 2d 2 delta d. Bring your lambda prime up here, then equated to 2 delta d, bring your lambda up here, plus lambda prime lambda. Or we can write as, now this is common, so if lambda prime minus lambda, bring over here, equals to lambda prime divided by 2 delta d. So in other words, delta d will be equals to, well, these two are very close. We can square that using one of the single lambda, one of the lambda. And here we have still have 2 delta d. This is a Gaussian diagram that shows the transition of different between different levels, and that will give you a photon of this particular wavelength. So the doublet are from here, and the difference in the wavelength is very close. All right, now let's go to another arrangement of the interferometer. So instead of allowing this to go to the mirror and come to this again, this go to another mirror and reflect back on its own path, now we tilt this such that when it's reflected, it doesn't come back to its own path, but it goes to sort of, I would say it's perpendicular to this beam to another beam splitter actually. And this one will be reflected by this, but not onto itself, but at 90 degrees, or rather, if you call this incident beam, then it's 45, 45, and then it gets reflected here. And when you bring the two beams together, you will have interference pattern. All right, now we go to another set of interferometer. In this case, all you need is just 2 parallel plates. So, but we introduce a air gap between these two surfaces, between these two plates. Now, light will enter at an angle theta t, it gets refracted, enter here. Now this is partially transmitting and partially reflecting. This inner surface is also partially reflecting. So you get multiple reflection here, but some of the amplitude or some of the energy of the beam, or rather parts of the beam, amplitude of beam would then pass through, likewise here and here, and they are brought to focus by a converging lens. And usually this surface and this surface are not parallel but tilted at a very, very small angle. Why we do that is to eliminate any fringe patterns that are not suitable, and because of these multiple reflections within the glass. Yeah. So now the spacing between of the air layer becomes a very important factor. And here you find is known that if the spacing is fixed, then it is called an etalon. Okay, etalon here. Here is how the pattern, how the fringes look like for a Fabry-Perot interferometer. And whether it's a dark or bright fringe, it will be determined by the path difference between successive parallel beams. And in this case, it is given by 2NF, which is a refractive index here, d cosine delta t. And we can we have NF, let's say if you take NF equals to 1, which is for air, because we're talking about air gap, then the condition for bright fringe would then just be 2d cosine theta t equals to the order multiplied by lambda. How do we get these concentric circles? Well, if we fix the gap distance, kept the gap distance fixed, and if this equation is satisfied at particular angles, then you'll find that you get concentric rings like that. And we have equation 3 here. What is the Fabry-Perot interferometer called if the spacing is fixed? Now the answer was just in the previous slide. Yeah. Now over here, just a simple setup to show you how we can we can disperse the output actually. So if a source has two wavelengths and the output can then appear as superposition of a double set of fringes. So what you get right after here would then be the double set. And in order to see the fringes clearly, we have to then split this setup because we're talking about two wavelengths. So if you can disperse it such that one set of the fringe will be slightly displaced. It is displaced from the second set, then you can see it clearly. So what we do is we let the output light beam pass through a prism, and then you will be able to see different sets of interference pattern. For example, you can see fringes for red, fringes for green, and fringes for violet.
Here are the learning outcomes for this lecture.